Hello. Welcome back to Chem 161, where we are going to basically be doing Chapter 3 for the rest of our lives. That's just how Chem 161 works, is we're here forever. We did the introductory part of the chapter, which is basically, here's a bunch of weird stuff that light does, and we don't understand any of it. When I say we in that context, what I mean is people in the 1910s or so when this was being investigated. Nowadays, we actually have a very good understanding of how light and electrons behave. But at the beginning of the 20th century, so like 100 years ago, this was all a mystery to people. In fact, it's kind of amazing to reflect on just how far we have come in a century. I actually was linked to a video of, like, somebody had remastered a video that was taken in 1904 in San Francisco, and it's just a bunch of, like, horse-drawn carriages swerving all over the road like they're insane. And I'm like, wow, yeah, that's about how I remember driving in the Bay Area in 2000. So some things don't change, but it's really interesting to see progress throughout the ages. And we are seeing that in this chapter. So we've gone from the conundrum of light, why does it behave how it does, to some deeper understanding as we progress forward through science. And the most important discovery that we're going to discuss today, actually, is something called the Bohr Model. The Bohr Model was a prediction that helped put together nearly all of the phenomenon that we talked about earlier. Some of those phenomena, like photoelectric effect, we're going to talk about that in more detail with other things, but like the line spectra, where do line spectra come from? Why is the hydrogen one so distinct? What does it all mean? Why does light behave like an individual photon, and what is it doing to the atom? And Niels Bohr came up with an idea, and he set out to try and solve an equation that would predict this. And the equation that they did by hand is just like, I don't know how they did this, but they did. They just crunched numbers until they found it. And so that's what we're going to talk about today. So the first thing I want to show is what happens if you put a sample of hydrogen through a prism. In fact, what I'm going to show you is this experiment in a link that I took. And I'm actually going to use this link for next week's lab. So let's see here. I want to go to YouTube. And I have a playlist that should be hidden. Yeah, lab number 3. Oops. So you can hear the guy talking because I haven't actually... Let's see here. Is this the right window? Yeah. All right. So this is actually going to be a link for next week's lab. And I'm going to mute him so that I don't get a copyright claim if YouTube is scrubbing for audio here. But what he's going to do, and you can see this here. Well, you can't now because the title card is in the way. He's going to take these lights and put them in this machine right here. And that's going to send a current through the devices. And inside each of the tubes is a gas. So like gaseous hydrogen, or gaseous neon, or gaseous xenon, or even gaseous like CO2 or mercury vapor. And what's going to happen is when he puts them through this thing, this is called a diffraction grating. And what it is it's a bunch of lines that are very narrowly spaced apart that when light passes through them, it causes the light to bend based on this wavelength. He's going to put this in front of the light that we see coming out of this device right here. And you're going to see all of the colors that make up that object. So if it's just white light, like this light right here, when you put the diffraction grating in front of it, and you could probably kind of see this already, it's going to make a rainbow, because all of the colors are mixed in light. So this is what that looks like. And so you can see every color diffracted from the source of light. It's coming through the screen, so it's coming straight at you, and then it hits the screen, and then it bends in both directions, because it bends randomly. It either goes left or right. And based on the wavelength, colors with higher wavelengths, which means their frequency is lower, bend more. And waves with lower wavelengths, so higher frequencies, bend less. And so they spread out so that you can observe them. And so he's going to change this by putting the device in the front of that sample. And then I think he turns it off. And I don't remember what order he does these in. I'll just fast forward a little bit here. There we go. This is probably xenon. Maybe it's not xenon. Maybe it's nitrogen. I don't know. Anyway, when you put the diffraction grating through this could also be mercury. I really only recognize like 2 of these. So, come on, put the fraction. There we go. That's what I wanted to show. So when the diffraction grating is put in front of this, you'll notice that only certain colors show up. And the colors that we observe from this sample are this dark blue, this green, and this yellow. Now, there aren't specifically any red or purple or I guess I'd call it cyan. So like this cyan that you see is actually a combo of different colors. But only certain colors appear, and that's interesting. Scientists thought that that was very unusual. Why are only certain colors appearing? All right, let's go to the next one. I think this is helium. Yeah, this is definitely helium. Well, maybe. Anyway, you see lots more colors in this sample, as shown. I keep saying what I think it is, and then I look down at the bottom, and it says, here are the 4 gases, and none of them are what I think it is. So in helium, or whatever this is, there are tons and tons and tons of available colors. Well, that's interesting. Why might that be? Why did the first one only have 3 colors, and this last one has tons of them? This one's definitely neon, I know that, because it'll be yellow, red, and then there's like a green line. Yeah, there we go. So in neon, you can see that specifically I'm getting a bunch of colors that are all bunched together, and then there's a single green line over here. There's nothing else past that. And then I do remember the last one that he shows is hydrogen, and hydrogen's the most important one. So here's hydrogen. And here's what hydrogen looks like when you put the diffraction grating in front of that. Is there a blue line? So that's actually something I do want to talk about in a second. I don't actually see a blue line here. I went back. If you see one, then that's cool. I'm going to guess that it's this, but to me that actually looks like an artifact. I don't actually see it. I see this green line, and that's it. Anyway, I do want to go back to this really quickly, because on this hydrogen lamp, it turns out that there are only 3 lines. There's this red line here, and this is actually a reflection of that red line. There's this light blue line, and then there's this dark, dark blue line. And it's very, very difficult to see, and I know that this is here because I've studied this before, but there actually is another line right here, but it's sort of in the UV range. Man, you guys must have better eyesight than me, or I'm just, like, have glare or something. But I actually don't see it. I wonder if I could see it in the playback. I'm going to have to look at this later. No, I totally don't see it on this for neon. Anyway, I'm going to unlock this video for you guys to see. This will be in the playlist for next week's lab, because next week's lab is going to deal with spectroscopy using these light-emitting devices, and this video will be available for you. But what's important here is that we see specific colors, but the other colors aren't there. And the arrangement of those colors gave some insight as to what exactly was going on. So when we look at the waves that are diffracted from our sample, we notice that certain colors appear consistently for a given sample, and that they have this particular spacing to them. And that spacing is actually going to be very important. So, like, if I were to take this thing right here and then rotate it so that it was, say, I mean, let's go to the sample window here. I'm going to put this here, and then what I'm going to do, I got to get to Photoshop real quick, is I'm going to, where's my cursor? So I'm going to take that thing, and I'm going to rotate it so that it is horizontal. By horizontal, I mean vertical, because I get those mixed up all the time. And I'm going to do my best to match up the colors here. But I'm going to put the red guy down here. And then I'm going to put the cyan guy, like right here. And then there's a... They're more purple, actually. Let me get towards purple. Then I got this, and then this. And so this diagram is actually going to come back in a little bit. Okay, so just keep that in mind, that this arrangement of colors is actually not random at all. We're going to come back to this diagram very shortly. Now, in the previous lectures, we talked about that elements have line spectra, and we learned that light has wave-like properties, but it's also quantized. It emits photons. Light comes out as photons that have specific energy. Now, could these concepts be connected? No, the answer is no. We're just going to move straight on to chapter 4. Said nobody ever, right? Like, absolutely not. These concepts have to be connected. There has to be some idea between a photon of light having the correct energy and these colored lines that are appearing. Because if I energize something over here, and I just give it all the possible energies, and I don't get a continuous spectra, something is prohibiting certain photons from coming out, and only allowing these 4. What is that? And that was Bohr's mission. Bohr tried to figure out where the heck are these photons coming from, and why are they so specific? And so he came up with this idea. We're going to go back to this screen here. And I do want to put the statement on here because this is important. I got to make it smaller for just a second. All right. And so this is what Niels Bohr thought. Niels Bohr said the following. Well, wait a second. Let's suppose that this diagram that we're seeing down here is the nucleus. And around the nucleus, I would have electrons that can go anywhere that they want to around my diagram. But let's suppose that on average, they spend a specific distance away from the nucleus, or they exist a certain distance away. And we're going to call these regions that they can stay in levels. And so let's suppose that my electron, which is right here, we're going to take him and just put him on a level. And so let's suppose that my electron just stays here in the relaxed state. So like as you would find this atom, normally the electron is just here. It's about this distance away on average. Then let's suppose that I do the following to it. I hit that electron with a photon. What does a photon contain that it could transfer to the electron? I'll give you a hint. I wrote it H nu for a reason. What is contained by the photon that will hit the electron and do something to it? Yeah, it's totally energy. There you go. Now, if I give something energy, it has the potential to use that energy to do stuff. Now, I've arranged the diagram in this manner to make an analogy. In the nucleus are positively charged things, which are pulling the electrons towards them, right? In the same manner, it's like how the Earth is pulling you towards its center. But you don't fall through the Earth because you are standing on the ground. Right here, my electron is on its ground. It's in the ground state. But if I gave it energy, I could push that electron to a new position. So if I give it energy, I apparently gave it energy. Let me try that again. Yeah, it's the normal force that prevents you from hurtling towards the center of the Earth. So if I give my electron energy, it will go up to a new level. It's kind of like you have something on the ground and you give it energy to pick it up and put it on your counter. Now that object has that potential energy. Just like this electron has that potential energy because it's further away. We lifted it up using the energy from the light. But now, if my electron tries to relax, the conservation of energy says, okay, you're allowed to come back down, but you must release the energy that you absorbed. So if I go down, that energy must be released. And when I release that energy, there's only one mode that the electron has, and that mode is to release that energy in the same way that it got it. And because this energy is released out of the system, then someone over here, such as us, we could see it. So for this specific transition from this level to this level, we created this specific wavelength, which we saw. And it turns out that depending on how much energy is pushed out when the electron transitions, you get a different wavelength. Because this axis right here, I'm going to try and write this sideways. It's really hard to do it on the pad here. This axis is increasing energy. So different transitions will lead to different colors. For example, this transition right here was enough energy to be a red photon. If my electron had instead gone to, say, let me do a different color here. From this level to this level, then this would be a different photon that would be a different color. And this might be the blue one, and then the next one would be the purple one, and so on and so forth. This one right here, the second one, is higher energy because it fell further. So this was Bohr's theory. He thought, okay, if electrons can live in specific regions, and we treat those regions with their attraction to the nucleus sort of similar to how we are attracted to the core of the Earth, we're being pulled down towards the Earth, then we can say that electrons absorb energy from light, or electricity, or whatever, and release that energy as light, because that's the only thing they have. And when they do that, we see that light. So what we see in these diagrams right here, so if I go back to the previous slide, what we see is the result of electrons falling down. And if we can use these lines as a sort of pattern and figure out what's going on for this atom, presumably we could figure this out for every atom. So let's work with hydrogen because it's the simplest. It's just one proton and one electron. And try and figure out the relationship, and then we'll move on to helium, which is 2 protons and 2 electrons, and so on and so forth, and we'll see what's going on. All right, and so this slide just tells you what I showed you on that diagram. So when energy is added to an electron, the electron will jump to a higher level. When the electron falls back down, it has to get rid of that energy, and it's released in the form of light. Now, if I drop something on the floor, the potential energy of the object is turned into kinetic energy. Electrons already have kinetic energy, and it doesn't really make sense to give them more because that would potentially just excite them out of the atom. So the energy out that they use is light. So that's what we're trying to figure out. We're going to try and figure out where these energy levels are in certain elements, or maybe even in electrons. So at this point, they didn't know. Did the electrons have the energy in them, or was it just the atom had a specific potential, or what? And that's where we're going with this, is those lines on our picture here correspond to something. So the lines that are going horizontal here, these right here. So this red line, this blue line, and these purple lines. Because remember, these were the lines that we saw in the spectra. Oops, I'm not on the right screen. There we go. Now, these energy levels that I had drawn, I just drew the lines as shown without numbering them, because it turns out the bottom number that we had was actually 2. But there is an energy level for each line that we saw on the spectrograph, the line spectra. And the reason that we see those lines is because certain transitions result in photons with the correct energy to be visible. So for instance, if I have something falling from 3 to 2, like I showed on the other diagram, the light that gets given off has 656 nanometer wavelength. Or 657, sorry. Close enough. If I fall further than that, so if I go from 4 to 2, then the light that's given off has a lower wavelength because it has a higher energy. And then finally, if I fall from the highest level, right here, n equals 5 to 2, then the light that's given off has an even higher frequency and higher energy. Now, does the energy only go up to 5? Actually, it turns out there are more energy levels than are shown on here. There is a 6, and a 7, and an 8, and a 9, and a 10, and an 11, and it turns out it goes all the way to infinity. Now, infinity is not an infinite distance away. It turns out that these levels get closer and closer and closer and closer together. The reason for that is because the nucleus can only hold the electrons so much. So if n equals infinity was infinitely away, those electrons would never see the nucleus, and they wouldn't be attracted to it, and it wouldn't be an orbital, in other words. But interestingly for us, if n equals 3 to 2, because I went from 3 to 2 here for this red guy, is a red photon, 4 to 2 is blue-green, 5 to 2 is purple, what do you think 6 to 2 might be, based on this pattern that you're observing here? So if I went from 6 down to 2, so this would still emit a photon, but it might be something like this. And that would be a UV photon, yeah. And that photon, very good, would be invisible because our eyes don't see it. So this is the reason we're only seeing certain transitions. There are tons of transitions. I don't have to end at 2. I could end at 1. I could end at 4. I could do any of these transitions that I want to. And in fact, in the next week's lab that you're going to do all the possible transitions between n equals 1 and 10. So 2 to 1, 3 to 1, 4 to 1, 5 to 1, 7 to 1, 10 to 1, and then you're going to do 3 to 2, 4 to 2, 5 to 2, and you're going to do all these calculations, which is like 60 calculations. But the caveat is I'm going to make you do it on Excel or on Google Sheets, actually. So, and teach you how to use commands to like just copy and paste your formulas so that you type it in the command one time and then you just drag it and it will paste it 50 times. And so it's a fairly easy lab, but you do have to learn how to use Excel and Google Sheets like the correct way. So like you have to make formulas and stuff. But what you'll realize is that even though there are tons and tons of transitions, only some of them land in the visible region. And those are the ones that you see. So it is possible for you to get transitions that are beyond vision. So you could get UV transitions. Or if I did something like, say, from 5 to 4, that's too little energy for us to see it. So this would be an IR photon. But if you have something that detects IR or UV, you would see it. And you would see these transitions, and the spectra would just be bigger than the line spectra that we saw. So this is what Bohr realized. He said, okay, we're onto something here. If I can assign these energy levels to numbers, and then look at the relationship between the numbers that are transitioned and the wavelength, then I will have the model for how electrons behave. And I will know what their energy is at all times. And so that's what he did. So working on this principle that electrons go up to a higher n because we provide them with energy, like electricity or something like that, and then they fall back down and emit light, let's try and figure out the pattern. All right. This slide basically summarizes what we said on the previous slide. Over here, you can see the extra line that's been added in for 6 to 2, 3 to 2, 4 to 2. Oh, actually, I guess this would be 7 to 2. But over here on helium, you'll notice that there are far more lines. And on barium, there are tons of lines. And you might look at that and go, well, where are all the lines coming from? Well, what do helium and barium have more of that might change how the energy levels are arranged? They have more electrons, so that's half of it. What else do they have more of? I gotta erase my wonderful diagram here. Not quite nodes, although that is correct. I'll give you a hint. It's a lot simpler than you're thinking. So you're in quantum mechanics mode. Think back to like chapter 1 mode. What does helium have more of than hydrogen? Besides electrons, protons. There you go. Yep, that's exactly it. Because what ends up happening is, and I'm going to zoom my diagram back up in here, is that if this is my hydrogen nucleus, and this is my increasing energy, I gotta tilt my paper a little bit. What ends up happening is that in the nucleus are protons. Here's my one proton. And my electron lives right here. And protons and electrons do attract to each other. So this proton pulls the electron towards the nucleus. But remember, the electron has kinetic energy, so it's moving around the atom and stays roughly this distance away. But if I move over to helium, helium has 2 protons. And if it has 2 electrons in it, and those electrons are equidistant, they're both going to be pulled to the nucleus, but the force pulling on them is tighter. And as a result, what ends up happening is that the energy levels change. So I didn't do this by mistake. I'm just trying to extrapolate this dotted line over. But all of the energy levels where the electrons would live are moved because the electrons are pulled towards the center by the nucleus. And so atoms tend to get smaller as you put more protons in them, but then they get larger for other reasons. And we're actually going to talk about this in much more detail later on. But suffice it to say that every combination of protons and electrons results in different ordering of energy levels. And so they will not have these fixed distances between them, meaning that we will not just see the same 3 colors all the time. What we end up seeing is what's up here in this diagram. Actually, I'll just put it on the screen here. What we end up seeing is what's on these spectra. Because as all the levels start to get crowded towards the nucleus, we have more and more possibilities for electrons to bounce between any 2 levels and end up in the visible region. So the more electrons and more protons you have, the more complex the spectra get. All right. Here's our diagram right here, shown with the energy level spaced out much further. And this is actually a closer representation of what the energy levels of an atom look like. We're going to assign some terms here to our features of the atom. And so I don't have a sideways highlighter, so I'm just going to highlight it like that. First thing we're going to do is define the principal quantum number. So we're going to call n the level that an electron could be on. Level 1 is the lowest area that electrons can reside in on an atom. If you give them energy, you can push them up to level 2. If you give them more energy, you can push them up to level 3, 4, 5, 6. If you give them enough energy, you could push them all the way up to n equals infinity, and then the electron is no longer part of the atom. You have ionized it, and this is how you make ions, to make them positive or negative. Now, the important features of the Bohr model are that, again, there are infinite levels, but they start very spread out, and then they squish together. For our purposes, we're really only going to show up to like 4 or 5, because the distance between 5 and infinity is very small. And past that point, it's not worth trying to draw where they go. And so when we draw this diagram over here on the left, or the right, sorry. Where's my cursor? When we draw this diagram over on the right, it should look kind of like what we just did over here. And so you can kind of see the resemblance, but I'm never going to be able to draw it as good as the book. And I guess I could just do... Oops, that's not what I want. I'm holding the wrong button, that's why. There you go. How did I do? Short answer is not great, but that's okay. All right. Now, I have no idea how they did this in 1910 or whatever it was. But my understanding is they didn't have calculators or good computers, or any computers really, in 1910, to do any of these calculations. And so they did all this by hand. Maybe with like an adding machine, I don't know. But eventually somebody realized that the relationship was the inverse wavelength. And now there's the constant. I didn't mean to put that up there. Is related to some constant times the inverse of the square of the energy levels that are involved in the transition. And that, to me, is insane. How the hell do you figure that out? I don't know. The constant that is involved here is called the Rydberg Constant. And you're going to notice that when we write the Rydberg Constant, it's capital R for Rydberg, but then there's a lowercase h. And this h is the symbol for hydrogen. And what this means is that this constant only works... Oh, I don't know what the hell that was supposed to be. This constant only works for hydrogen. Every atom has its own constant, and the constant is based on the effect of the protons changing the energy levels around. And all of those constants have been calculated for different atoms and can be looked up in tables. But for our purposes, we're going to only deal with hydrogen in this class. When you get to 361, when you do an entire class on quantum mechanics, and yes, there is a 10-week course on quantum mechanics. I took it, and I don't know how I passed it, because it's basically this, but with calculus and more stuff. You basically do this. You graph out all of the orbitals by using equations. It's called the Schrodinger equation, and it's insane. And this is how we basically discovered how electrons work. For now, we're going to stick with this simple equation, and I realize that I'm putting simple in air quotes here, to figure out the wavelength of photons that come out whenever you transition between these two states. Now, when you do this transition, you have to be mindful of what numbers you are entering in to this equation, because you want to have a positive number come out. So let's suppose that I have a 2 to 3 and a 3 to 2. This is actually the direction that my electron would go to release energy. When it is releasing that energy, it releases it as a photon. So where do I put the numbers? Well, if I put a 3 in first and a 2 in second, I get this number, which is 1 over 9, and this number, which is 1 over 4, and I get a negative number, don't I? Can't have a negative wavelength. That's not going to work. But if I switch the orientation of the numbers here, so if I put in the 2 first, that's supposed to be a 2. Let's try that again. I guess my brain went 2 squared is 4 and started writing a 4. Now you have 1/4 minus 1/9, which is basically just me swapping these two numbers around, right? And this gives you a positive result. And it even turns out that 1/4 minus 1/9 is just the absolute value of 1/9 minus 1/4. And so the take-home message that we have here is that the smaller n is going to be n1 when you use this equation. Because when you put the numbers in that way, you will get a positive number. When you put all these numbers in the calculation, you will get the inverse wavelength. Then what you need to do is push your inverse key on your calculator. So remember that when you have something that is 1 divided by it, that is the same as that thing raised to the power of -1. Now let's suppose that I took the inverse of this. That would be like doing this. When you have an exponent to an exponent, you multiply the exponent. So -1 times -1 would be 1, or just this. So if you take this result, 1 over lambda, whatever that number is, and you push this key on your calculator, raise to the power of -1, and that's why you have this x to the -1 button on your TI-83, you will then get lambda. So that's just an algebra trick for you to remember, so that when you punch all this in the calculator, all you do is hit enter, you'll get 1 over lambda. You then take that number and raise it to the -1 power, and you will get lambda. Now the units of your lambda will be in meters, because when you solve this equation, n doesn't have units, RH has inverse meters as units. When you solve for lambda, it will be in meters. So you'll have to turn it into nanometers in order to get a number that makes sense for photons. All right. This slide just tells you about how to use the equation in order to get a positive number. If you put the smaller n first, you will get a positive result. But using these equations for thermodynamics and energy considerations, the sign might actually be important. So for instance, if you were trying to figure out the energy lost by the atom, then you'd actually want a negative number, and then you should put n1 as the larger number. We're not really going to ever worry about that. We are only ever going to concern ourselves with this. But if you take a later thermo class and you're trying to figure out the energy change for a system, that information could be helpful for you. So we'll just move on. All right, let's do an example. What wavelength comes out when I transition from 3 to 2? And we already know the answer to this question because we just showed it on the diagram. And that was you get a red photon. Let's see if that's actually the case. Well, that's a whole lot of not helpful. Hold on. So I need to write down the Rydberg equation, which is 1 over lambda. Rydberg constant times n number 1 squared minus n number 2 squared. And I'm going to have my electron go. Here's my diagram here. So here's the nucleus. My electron is going to fall from 3 to 2. And I kind of missed my 2 there, but that's okay. And in doing that, it's going to spit out a red photon with wavelength lambda. And that's this lambda right here. So I got to solve for that. Now I do want to put the smaller number first in my n. So that's going to look like this. Rydberg constant, 1 over 2 squared minus 1 over 3 squared. And I've already forgotten the Rydberg constant because I never memorized this one for some reason. It's like 106,776. Let me find it again real quick. 1096776. So let me... Oops. I hit the space bar there. Can I get that on the screen so I can see it? No, I can't. 1096776 times 10 to the 7, right? Yeah. All right. Now I can put this back to the problem that we're doing. All right, and now all you gotta do is punch this in your calculator. So I will type in the Rydberg constant times parentheses 1 over 4 minus 1 over 9. And so this is what my calculator spit out. 1 over lambda equals 1523300 inverse meters. Now, how many sig figs do we get? These are exact numbers because these are counted. And the Rydberg constant is 1, 2, 3, 4, 5, 6, 7 sig figs. So I get to keep all of these digits. So I got to do that. Then all I do is take the inverse of this. And I get this. 656.4. Sorry, I went straight to nanometers. Hold on. 6.56469 meters. I forgot my exponent, sorry. So that's what my wavelength is in meters, and then when I change this to nanometers, I get this. I kept wanting to write it in nanometers so bad, you guys. There we go. So this is how the wavelength of transitions in the atom are determined, is by using the Rydberg equation. How do I find that in the calculator again? So I typed in this first expression right here, so I'll just put a 1 here. I put this in the calculator, and I got this number. And yeah, we are looking around the shells around the nucleus. And then, so I had 1 over lambda equals this number. I took the inverse of it to get this number, which is this in nanometers. That is interesting. Yeah, so I saw that and then the mass comment, and I was like, did I miss something? So I have no idea if the... Now I don't trust my chat window. That's okay, though. Your inverse is giving you a completely different answer. Well, I know that 656 is the correct answer, because that's the number that I quoted earlier. You do the to the 1 exponent, but make sure you're putting parentheses around everything. So if you're doing, like, Rydberg constant times 1/4 minus 1/9 inverse, it might only be inversing the stuff in the parentheses. So I just type in the whole thing, hit enter, inverse the answer, and you should get 1523300. We're going to take a break in a second here, so if you're stuck, and we can talk about it over the 10-minute break. All right, so that's how we calculated the transition for the red photon. You got 0.15233. Hold on. am not getting that number. This is where I wish I had a camera that I could just show you guys. So here's what I can do, though. All right, so here's what I typed in specifically. I just got to call it back up. So I typed this into my calculator. 1.096776 times 10 to the 7. So I typed that in times parentheses 1 over 4 minus parentheses 1 over 9 parentheses, and then I hit equal, and what it spit out was this. And then the next button I pushed was just this. I pushed that and I hit enter, and it tells me this. You got it. Did you get it, Firefox? If you have a button that says 1 divided by X, then that also works. Oh, are you using a Casio? You should have if you're using a Casio, you should have a button that looks like this. Or something like that. Press this button, and it will turn your fraction into a decimal. Good old Casio, because 1 divided by 1523323 whatever was exactly the answer that we were looking for. I love my fractions to be really big. Fucking Casio, I swear. Not your fault. It's Casio's fault for being stupid. Because we always want the decimal. X to the minus 1 should also work, yeah. In fact, that's what my button looks like too. It says X to the power of negative 1. But if you have a button that says 1 divided by X, that is also the same thing. There are so many calculators out there, y'all. Alright, what photon is this? Well, if we scroll all the way back and we look at the spectra, we would find that the 656 nanometer is the red one. And so to summarize, before we take our break, that the Bohr model and our Rydberg equation together explain why we see all of these lines for specific atoms. Electrons go between levels. When we excite them, they gain energy and go up. When they relax back down, they release light, and the light will be the Rydberg equation wavelength, or inverse wavelength, that we can then solve and figure out what its wavelength is, and then you can also figure out its energy. Because remember that E equals... Oops, that's my highlighter. So I can use the Rydberg equation to figure out this, but we also know that E equals hc over lambda, which is the same as me just saying this, right? So to figure out the energy of a photon, I just take the Rydberg equation and times it by hc. And so this will be the energy of a photon in joules for a transition that happens. Because this right here is this right here. Okay? So you might be asked to do that. But you could also just say, oh, okay, well, I'm going to solve for the inverse wavelength and figure out what the wavelength is, and then I'll just plug it into here so that I don't have to deal with tons and tons of algebra. It's simpler to do it my way, but you do whatever you need to get to the answer. I totally don't care. As long as you can get me the correct energy. For what it's worth, I believe the energy of this photon is like 2.1 times 10 to the minus 19 joules. Something like that. All right. We already talked about that it's specifically for hydrogen. I know that your textbook has an equation of this that has this in there. So it'll be like z squared over n squared, or n squared over z squared, or something like that. Very, 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 very important. These equations that have the z term will help you work for any element. And remember what z is. Z is the atomic number. But there is a very, very important catch that has ruined quantum mechanics for everybody. None of these equations work for any system with more than one electron. And the reason for this is because when electrons repel, they push each other apart chaotically. And there's no way to do a prediction for a system with 3 charged entities to a high degree of precision. And the precision goes down exponentially when you put 4 electrons, or 5, or 70, or whatever. You can sit there and let the calculator do the computation, and in fact, this is what graduate students do, is they run these calculation models where the computer just tries a number, and it guesses and tests, and it moves the result around, and you turn on the computer and you run the program, and then you come back a week later and it might be done. Because that's how crazy the calculation is. It takes a week for a supercomputer to do. So, at the current time, there's no way to calculate these answers. Yeah, it'd be kind of like a neural network if all of the entities in the network were working on the same problem. This is just a supercomputer, which is just a huge computer that can run a bazillion bits at once. And again, because none of that's useful to you, really, we're only going to work with hydrogen. So what I want you to do over the break is I want you to try and use the Rydberg equation to do n equals 4 to n equals 2. So quickly write that down. This is what I want you to do. I want you to calculate 4 to 2. And then hopefully you have the Rydberg equation in your notes. I'm going to put the title card up. We'll turn on the break timer, because it sounds like we need a break. I don't have a timer. Hold on. I never have a timer ready. That is the one thing I know. Smaller number goes first. Because otherwise you get a negative. Alright, so... Oh, wait a second. Sorry, quantum mechanics. We gotta do this one. That's just cruel. I'm just going to tease you with the daylight and then back to the darkness for you. Alright, where's my foreboding music? Ah, there it is. Ah, so close. One of these days. Are the energy states of electrons independent of orbitals, or are they the same thing? They're actually the same thing. So the energy levels of the orbitals are just the regions in which electrons settle into when they have energy. And in fact, orbitals are sort of this fictitious thing that we're making up to explain this. We're going to define an orbital later on as the space where the electrons live. But in reality, the electrons are the orbitals. They have the space that they occupy, and they are essentially the entire thing. All right, so let's write down the Rydberg equation again. So, oops, I've already messed up. And so that is this right? I had my calculator on, so I was looking at this number. 1.096, so yeah, that's right, okay. Times 10 to the 7 per meter. And I want to go from 4 to 2 this time. So that means that this will be first. And so when I punch that all out in the calculator, times... Oh, I messed up hard. 1.096. 776. I hit the wrong button and then I got very confused by what happened there. 4 squared is 16. Enter. And so I got this. So I'm going to invert that to get meters, and I got this. 4.862737 times 10 to the minus 7 meters. .2737 nanometers. That looks like what other people got. And what color is this if I do this to your screen? Which one must be forwarded to? It must be... Let's see if I can do this. Let's see here. This one. All right. So that is the Rydberg equation. And it turns out this slide is the end point for exam 1. So nothing after this slide will be on exam 1. Okay? So that's all the math. That's all the math we're going to do in this class. So that could be a relief for some people, or that could be awful because there's no more math. We are done with math. In fact, I'm going to take my calculator and I'm going to just throw it on the floor. And then I'm going to step on it a few times because I don't need it anymore. That's sort of not true. Like, we might use it to count, like, to 10 or something. But yeah, we're done with math. There is one equation that is coming up. It'll talk about the wavelength, and I will show you a problem just to show what that means. But I'm not going to test you on de Broglie wavelength, so we're done with math. So let's continue for the second hour. I don't know what time it is because my phone's on. I got to turn it off. My always on display I've grown accustomed to. I actually had to do that. There you go. So from this point on, this is exam 2 territory. And the rabbit hole goes really deep. So what we're going to cover in this section is what's called quantum theory, also known as, oh, this is that cat thing I've heard. Oh, the wood chipper is back. Why? I'm hoping that these people are done soon, but that's okay. All right. Did you hear my cat? Is my cat in here? No, okay. There's just the wood chipper is backing up in the parking lot, so. All right. What is quantum mechanics? Quantum mechanics is the field of study, and I think I summarized this last time as things are really, really, really freaking small, so they don't follow the regular rules that we thought. So classical mechanics is stuff that you're familiar with. If you throw a ball up in the air, it falls down. If you throw a ball at the wall, it will hit the wall, and you will know where it hit. When it falls on the ground, you will know where it is. You could measure how fast it's going. You could know all these things with certainty. And all these equations that we have worked with in like elementary physics classes deal with this field, classical mechanics. This is just how stuff works that we're familiar with. Quantum mechanics is the field of study for really, really tiny things. They don't follow classical mechanics. They follow wave mechanics. And what that means is that pretty much everything behaves like a wave at the atomic level. And those tiny particles behave differently than we would expect. And because they are so tiny, we don't have very many ways to analyze them. This leads to a lot of experimental error. For instance, let's suppose that you had a golf ball. Now, in classical mechanics, you could just observe the golf ball. You look at it, you could pick it up and throw it, etc. And then you could measure its properties. But in quantum mechanics, if that golf ball were actually an electron, the object that you would have to figure out where it is would be something like a bowling ball. You have to use the bowling ball, and when you hit the golf ball with it, that's how you know, oh, the golf ball was here. And that's all you get. You don't get to see it. All you get to know is, oh, I threw the bowling ball and I hit a golf ball. And that's the information you get. You might throw the bowling ball a second time back where you threw it, and now the golf ball is gone because you hit it. With electrons, it's the same way. If you hit an electron, because electrons move really, really fast because they're really tiny, if you hit it with light, you move it. And now the electron is gone, and we don't know where it is. It's somewhere else. Not only that, if we try and figure out properties of these components, we change them in the nature of doing so. Which leads to the Heisenberg uncertainty joke that somebody is going to tell you in just a second. I should get my Price is Right horn ready for that. But let's talk a little bit about how waves behave, because we need to have a little bit more detail before we can start assigning these properties to electrons, because electrons, spoiler, behave like waves. So the first property we want to talk about is interference. If you have multiple waves and you add them together, their peaks and valleys add to each other. If the peaks line up, they get taller. If the valleys line up, they get deeper. But if a peak lines up with a valley, they neutralize each other out, and the result is 0. So this wave on the left here, I have maxima lining up with minima, and so those maxima and minima expand. But if I line the maxima with the minima up, I get 0. So if you have two waves that perfectly desynchronize each other, you get nothing as a result. Probably the best phenomenon that I can think of is if you've ever been in a lecture hall, and I mean like a big auditorium, and you stand in a spot that's kind of next to the wall, one of your ears might hear less than the other ear. And the reason for that is because the waves in the spot that you are at are bouncing off of opposite walls, and when they line up to get to your ear, they have neutralized. And so this is known as acoustics. When you go to like a concert or something like that, something that is always done is they do an acoustics check. Somebody walks around the room with a sensor, and they listen with their ears and use the sensor to figure out, are there any dead spots in the room? If there are, they don't put a table there or have people stand there, because if you go to a concert and you're standing in a dead spot, you're not going to hear all of the music, or you're going to hear something. It's just going to sound wrong. And as an artist, you don't want the music to sound wrong to your audience. And so people pay a lot of money to figure out places that are dead spots in their lecture hall, auditorium, concert hall, etc. Now with light, the same thing is true. And I think I have a link for this. Where's my link? There it is right there. Okay. So I'll get to that in a second. All right. The next property that we're going to look at is something called a slit experiment. And what this is that when you have... Oops, sorry, hold on. When you have a barrier that has a gap in it... Oops, I couldn't find my cursor. When you have a barrier that has a gap in it, and you have particles that are shot at that barrier, if they hit the wall, nothing happens. But if they don't hit the wall, they go straight through. Now with waves, it's different. With waves, the wave direction will move in this like this. Then the waves will reflect and go backwards, unless they pass through the slit here, in which case they diffract around a corner. And you get a sort of cone going on here. And I do have a video for this. I need to get my cursor back. And so you can see, and I'm going to try and like frame forward, frame backward here. I'm doing this one frame at a time. So this is the gap that is in the middle right here. And my waves are going through that gap, and they're sort of turning a little bit. It's hard to really see the diffraction unless I have it moving, but it becomes much more obvious when the gap is narrowed. So you can see that my waves, and this is just water waves, with a device on the left here that's going doot, 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 and tapping the water and making a regular wave here. YouTube, stop buffering. Okay. This next experiment that we have here is with two waves. And as you can see, when the waves cross over each other, they have valleys, which are these dark regions here, and peaks, which are the light regions here. But when two waves cross each other, you get this sort of checker box pattern, where part of the two waves added together here, but they subtracted away together here, and you get nothing. Let's just hit play on that. And now this is true for any types of waves, so if you have a circular wave or a flat wave, it still behaves the same way. Alright, so... Oops, that's the wrong video. I don't want that anymore. What does this mean for us? What do we care? Why do we care about how waves behave? Well, we're going to do an experiment. And the experiment is this. We're going to do that double slit pattern. And we're going to let our source of whatever. So here's a light source. And the light source is going to beam through our two slits. And that's going to hit this detector, which is labeled film right here. And so, oops, when the light hits the film, anywhere where the light has added together is going to show up as bright. So these bright spots are where the waves added together. The dim spots are going to be where the waves canceled out. And what ends up happening is that we get film that looks like this right here. And this is called a diffraction pattern. In other words, if I aim something at this pair of slits and it registers on the film as a diffraction pattern, what I fired through was a wave. So we know that light behaves like waves. It makes a diffraction pattern. Therefore, that's our conclusion. If I can fire something else that'll react with the film through this, it must be a wave. And so the experiment that was tested was, okay, I'm going to fire electrons. And I want my electrons to go through this, because electrons are individual discrete things, and I can fire them through a beam. And if my electrons are particles, they should just go straight through. They will hit the detector in one spot, and then everything will just be hunky-dory. And we'll have this great proof that electrons are just particles, no big deal. And so they did this experiment, and guess what the result was? So here's what I'm going to do. We're going to put this guy over here. All right. So this is what we would have expected for particles. The particles would just go straight through the detector, and we would have two bright spots because electrons just would travel in straight lines, just like what I drew. This experiment was done in the 1920s, and guess what the result was? That's not at all what we expected. Why did electrons do this? Why are the electrons behaving like waves? Because it turns out all matter behaves like waves too. And that's weird. That's very strange. Why do waves act like particles and waves? Or, I'm sorry, why do electrons act like particles and waves? I thought that this was just going to be about light. Why does everything have the wave-particle duality? Well, it's because all small objects are weird. There you go. It's weird. Hooray, weird. No, it turns out everything does this. It's just that we're going to see in the next section when I talk about de Broglie wavelength. And yes, it's an equation. I'm not going to make you do this one. We're going to learn that the wavelength of big things is super tiny. And it's so tiny that you can't observe it. Whereas the wavelength of tiny things is observable. And so the wavelength of any particle with a known mass is given by this equation. So this is Planck's constant. This is the mass in kilograms. And this is not frequency. This is why quantum mechanics is obnoxious. Well, this is one of the reasons, I guess. This is how fast the particle is moving, which is a velocity. Now, the units of this equation are a nightmare, which is, again, great that we don't have to worry about this. I'm going to work this out anyway. The units of Planck's constant are joule seconds. The units of mass are kilograms. And the units of velocity are meters per second. And you'll notice that nothing cancels out until I do this. A joule is a Newton meter. And this is my second from over there that I need. And a Newton is actually a kilogram meter per second squared. I'm going to times that by this meter right here, which is this. I'm going to times that by this second right here, which actually cancels this one. And then down here, I have kilogram meters per second. The kilograms cancel. 1 of the meters cancels. 1 of the seconds cancels. And the unit that's left over for wavelength is meters. I said you're done with math. I'm not done with math. I'm just using this to explain. We're not going to use this equation, but I'm going to explain the philosophy behind it. So now that I've proven that this is actually in meters, you can just trust me on it. You're not going to have to calculate this, but I do want to use the equation to prove something to you. And that is that the wavelength of something that is visible to your eyes is too small to ever observe. And so if you looked at a classical particle like a baseball, we're going to use a baseball as our example, and you throw it, you'll never see its wave because the wavelength is just so small. But if you throw an electron, its wavelength is large. And thus, the conclusion that we're going to draw is that anything that's macro scale, even though it does follow wave properties, we're going to treat it as classical. But anything that is quantum, we can't define specifically where it is because it has a waveform. All right. And then again, that's Planck's constant. So let's figure out the wavelength for this. And again, you don't really need to write this down. You just need to write down wavelength of electron equals determinable. Wavelength of baseball equals not, or something like that. But I am going to show you the equation. Oh, I'm holding the Windows key. That's why that's not working. I have to hold Alt to resize the box. And if I hold the wrong button or no button at all, it will just make the whole thing bigger. Delete. Alright, so the wavelength is going to be h over mass times velocity. Suppose an electron is moving this fast. So this is the speed of the electron. And then I got to look up the mass of an electron. I think it's this. Let me look that up real quick. Mass of electron, kilograms. 9.109 times 10 to the minus 31. Okay, cool. I never use this number, so I'm actually surprised that I know that. And when I punch this in the calculator, and again, you don't have to do this. You are not going to have to do this. I'm just showing you how this calculation would be done. Yeah, don't panic. I know. I just said that you don't have to do math, and what are we doing? We're immediately doing math. And the reason for that is this equation is just not super useful to you. So again, all these units are going to cancel out. And we're just going to have meters at the end, like I showed you earlier. And here's what the wavelength that I get is for this. 2.74. Which would be that. Now this we can observe. Uh, 3.1 and 3.2, but yes. Okay. So this is a value that we could observe because 0.2 nanometers is a photon that is not that much smaller than the photons that we've been using so far. Now, it's smaller by a factor of 1,000, but that would be like an X-ray or something. So this is something that exists. But for the next problem, we're going to learn that the wavelength of this baseball is a little smaller. And so we do the same equation again, h over mass times velocity. That checks out. I believe that. What was my mass? It is 0.150 kilograms. And I'm throwing it at 11 meters per second. And you can right away see 10 to the minus 34 divided by tiny numbers is going to be stupidly small. Oops, that's not a parenthesis. 11. All right. Do we even have a metric prefix that goes down to that? Something that has a wavelength of times 10 to the minus 34 meters? And so what this means is that the takeaway here is large objects oops, let me not do it this way. Now, so large objects have impossibly small wavelength, and so they obey classical mechanics. Yeah, I don't actually know. I have memorized down to like femto because there's like atto and yado or I don't know. Oh, I've heard of the Planck length. It's just, what do you use that for? I don't actually know the answer to that. So large objects have impossibly small wavelengths, so they follow classical mechanics. But atomic objects... And so anything that's not an atomic object is a large object for the purposes of this discussion. So like atoms, electrons, protons, neutrinos, etc. And I'm almost reluctant to put atoms in here. I'm not sure if that's small enough. They have an observable wavelength, and because of this, they follow quantum mechanics. Okay? And that's all I care about the de Broglie wavelength. We're never going to use the calculation again. But because we could see that these numbers, one of these numbers is small enough that we can work with it, or large enough that we can work with it, but the other number is so tiny that there's nothing that we can do about that. What is a neutrino? A neutrino is a very, very tiny particle that has no charge, but has an incredibly small mass. So it's like an electron with no charge, but I think it's smaller than that. That is actually all I know about it. I know that if you collide two atoms together and you do fission or fusion, one of the results can be neutrinos. And because it's so tiny, it passes through virtually everything. There are ways to detect it. They generally involve like giant tanks of water with fluorescent things in it, and if a neutrino strikes it, then it lights up. Could an object be moving so fast that it doesn't have an observable wavelength? If you increase the speed... I gotta look at the equation. Hold on, let me think about this. So if this goes up, this goes down. Yeah, so if you accelerate something super fast, its wavelength should go down. Remember, there is a speed limit, though. You can't go past the speed of light. And this number that I put in here was remarkably close to the speed of light. It was 1% of the speed of light. 1% of the speed of light in the grand scheme of things is remarkably close. You can see light waves, but light waves don't really have a mass associated with them. So this formula becomes a little bit different. Yeah, because 3 times 10 to the 8 is the speed of light. Approximately 3 times 10 to the 6 would be 1% of that. You will not use this equation in 162 or 163. It is exclusive to just this chapter. All right. The only purpose of all of that was to get this differentiation here. So again, microscopic teeny tiny particles have observable wavelengths. Macro scale objects do not have observable wavelengths. And so what does that mean for us? Well, the first thing that we're going to talk about is how to manipulate this, or at least try to. And so what I should have done is I should have done this and said, let's suppose that we put an experiment here. And what the purpose of the experiment is to have a laser that when the electron passes through it, it hits the laser, and then we know which of... This was the wrong color to use here. And why am I using the mouse? Ah! I thought I disabled that. My laser, the objective of the laser, is that when my electron goes through, it should strike the laser. And then I will know, based on the physical location in space, which slit it passed through. And then because it's acting like a wave, presumably from here it will just go like this and make a diffraction pattern. Now what's interesting about this is that when we set the laser in the way, the result that we observe is that the electron is now behaving like a particle. And so over here, it is a wave plus a particle, and it goes through the slit, and it goes through whichever one, but it still behaves like a particle and a wave. But once it's hit this, we have learned something about it. We have learned where it is. We have collapsed its position. And if we know where something is, it behaves like a classical particle. And so it hits the detector straight on. It's no longer a wave because we learned about it. What? And this is why quantum mechanics is weird. Because as soon as we learn about something, we change the nature of that something. And thus, any further analysis that we do of it has pretty much... The word that I want to use is corrupted. Like, it is no longer in the initial state it was before we observed it. By hitting this laser, the electron has changed in some fundamental way. And from that point on, it is no longer the same electron. Destructive measurement is a really good term for it, because before and after, it is not the same thing. That is a good analogy, unless you're very careful. But yeah, if like you open the door and it wakes your parents up, just the act of doing the observation changes the outcome forever. And so this is called the uncertainty principle. And what the uncertainty principle says is it's basically, I have some state beforehand, and when I make an observation, two things happen. I learn something about the substance, but the old state is lost forever. And this would be like, let's suppose somebody gave you a birthday cake, and they put it in a box, and they brought it to you and said, "Happy birthday, I bought you this blue cake. I mean, maybe it's red." And so you ask them, well, is it red or blue? And they say, well, it's both until you open up the box. And when you open it, it will be one of those colors. Now, if you're listening to me say that, and you're saying, wow, that's like the worst analogy Wes has come up with. I've heard that he has bad analogies, but that one's stupid. It turns out this is actually the best analogy I have, and it's on purpose, because this is what quantum mechanics is. I don't know what's going on in here until I look at it and make an observation, but by doing that, I destroy the original thing. And this made somebody really, really mad, and his name was Schrödinger. And you've probably heard of Schrödinger, and probably more importantly, about his cat. And this is called Schrödinger's cat. And so Schrödinger's cat is the following postulate. And Schrödinger proposed this because he thought this was stupid. Okay? So it's really important to keep in mind that this is not something that Schrödinger thought seriously. He thought this was stupid. He said, okay, in a box is a cat. And here's my cat. I'm trying to draw it really quickly. And the cat is in a box that contains a vial of radioactive material. So here's my vial. It's got the radioactive material in it. And there's enough material in there that will kill the cat. Okay? Now, we obviously don't want that. So I'm going to put this in a container that is closed. But I'm going to attach it to a button. And that button's going to be attached to a hammer. And the hammer has a 50% chance of hitting the button to release the radioactive compound, which would kill the cat. And now what I'm going to do is do this. I need to make a new layer. I'm going to put this in a box. And until I open the box, I don't know if the cat is alive or dead. Because the box is closed now. Oops, hold on. I gotta rasterize this so that it'll let me type. Okay. Until the box is opened, I don't know which of these is correct. At this current time, they are both correct. But the second that I open the box, boop, now I have gained information that changes the outcome. No, you can't do this to a cat because this is a thought experiment. So now that I've opened the box, I know that this is true. But when I have the box closed, I don't know which one is true. The act of me opening the box changes the information that I have, and the words he uses collapses the wave function and creates a reality. But before that reality, both are true. And Schrödinger said, so this is all his thought experiment. He said all of that stuff, and then he followed that with, this is ridiculous. Like, it is absurd to believe that this is what we are suggesting is happening at the atomic level. And guess what? This is what's happening at the atomic level. This is why Schrödinger was so upset. Because he was saying, okay, this is basically just chance what happens. Everything is just random. And you might have heard the famous expression from Einstein, God does not play dice. It turns out that God plays dice, and not only that, the dice are loaded. Caveat, I am not religious and don't endorse any specific religion. That is just a quote that I took from somewhere, and I thought that it was really fitting. So, what does all this mean? What the heck does this mean for us if everything is just random chance? And that observing stuff creates the probability of that state to be 100% and all other properties are 0. Well, what that means is that we have to start making assumptions about how matter behaves before the dice literally explode. In Shadowrun, that's the thing. Your dice are supposed to explode. That's a good thing. If you get a 6, you roll again. What this means for quantum mechanics and for our study of it is that when we are looking at stuff, we have to assume that both properties exist, but we don't know anything about one or the other. And so there's an equation that regards this. I'm going to skip over it. But this principle is called the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle states that for any system, such as an electron, if you have two properties that it simultaneously has, you can only ever know one thing about it. The other information is lost. For example, if I have an electron and I want to figure out where it is and how fast it's moving, this is what I could do. So here's my electron. And I am going to use light to determine where it is. Bonk. And when I do that, the electron now goes, whee! So I would know, oh, it was right here. But how fast was it going? Well, I would have to do a different experiment to do that. And now I would get its speed over here. But its speed over here was lost forever. So I can only ever know one thing at a time. Because when you do your experiment, you change the nature of the object in an irreversible way. And the joke that we have for that is that Heisenberg was going down the highway, and he gets pulled over by a cop. And the cop tells Heisenberg, "Do you know how fast you were going?" And Heisenberg says, "No, but I know exactly where I am." And then the cop says, "You were going 83 miles per hour. And Heisenberg says, "Well, thanks a lot, officer. Now I'm lost." I have a student who's going to type that out for me. Oh, I beat you to it. I'm sorry. This is why I have an advantage. I'm 20 seconds ahead of you. I'm speaking to you from the future. Yeah, that was a really bad joke. Hold on just a second. I believe that I deserve this. Oh, I had it muted. Hold on. Yep, there we go. All right. Now, the takeaway for this is that if something has the properties of a particle and a wave, you only get to learn about one at a time. And that's the nature of quantum mechanics. Everything is so tiny, and it has multiple properties, but you only ever get to learn one thing about a system at any given instant. You could measure it at the start of your experiment and then measure it later, and maybe do that a million times, measuring different properties and then take the average. But for any given system, at any given one individual instant in time, you can't get both properties. So what that means, we're going to skip this formula because I don't care. We're going to go straight to this. What this means is that if you are an electron and your electron is moving, it's impossible to locate where the electron is. So I cannot just draw a line and say, this is where my electron went when I threw it around the nucleus. What I instead have to do is draw this region and say, my electron is in here. And by doing that, I would say my electron is not out here. And you would assign that a probability. And what this right here, is the Electron Cloud, which we talked about in Chapter 1. Now, it is kind of like a bell curve, and you can see that the darker stuff is in the middle here. So you are more likely to be along the line, but you are not guaranteed to be along the line, because remember, it's a wave. And I'm using the wave as kind of a loose analogy to help you understand like that, because the electron moves in a very irregular pattern. It doesn't move like a wave like that necessarily, but that's the best way I can think of it demonstrating. No, the darker color is actually just, it is more likely to be there. Each of those little pixels is a dot that represents, hey, I found an electron here when I did this experiment. And wave-like is proper, yeah. So when we discuss electrons on Tuesday next week, we're going to start talking about orbitals and where electrons live. But whenever I say the word where an electron blank, remember that it is just an assumption using quantum mechanics. I know it's in this area, I don't know where exactly it is, but I'm just going to treat this whole region as my electron. And so when we start talking about s orbitals and how it's a sphere and the electron lives somewhere in the sphere, the s orbital is just where the electron is. And that's what quantum mechanics wants you to learn from this, is we don't know exactly where the electron is, it's somewhere in this spot. And so that's what this discussion is, and that's actually where we're going to stop. So we're going to talk about orbitals on Tuesday. But in the last few minutes, what I do want to talk about real quick is the exam. Here are some points that oops, sorry, I'm stretching. I should just wait. Here are some little caveats and points that I want to make about the exam. So the details of the exam. And I guess I'll write this down so that you have it on the screen. So let me do this. We will kill the cat by erasing it. All right, so exam 1. So there will be strictly multiple choice questions. And I'm going to choose those questions randomly from a bank of a lot of questions, which I'm going to program, okay? So what that means is that if I program 60 questions in there, you are going to get 15 of them, just randomly. And your 15 questions will be different between attempts. They may be mostly Chapter 1, they may be mostly Chapter 6, they may be mostly Chapter 2. It's random, it's quantum mechanics. So the only real way to be able to answer all those questions is to know everything, basically. So make sure you're studying the slides, make sure you're studying the text, make sure you've done as many practice problems as you can. But each of those questions is worth 2. I'm trying to do math in my head. Hold on. That's not the right number. 50... 75 plus 7 8 is 83. Okay. The remainder of the points are going to be from other question types. And this is really important. These questions are going to be extremely similar to your quiz questions in the sense that I might even be using the quiz questions in some cases. Okay? So if you have done all of your quizzes at this point, which you should have, you will have your answers in your work. And a lot of these questions are going to be very, very similar. I'm going to make minor edits to some of them because, for one, I don't want to go back and regrade all of the partial credit on quiz 1. So I'll just edit that. But if that question gets into the exam, you'll see it again, and it'll be in a different form, and you'll have to do something. Okay? Some questions will not have partial credit associated with them, so you'll just have to be careful. But these questions will be deterministic. They will be like the quizzes in the sense that you will have a question type, and it will come from a pool of 3 potential variations on that. And so every time you will see one of those. But up here, these multiple choice questions will be randomized. The other things to note are the following. So you'll notice that the total is 83 points. Only 75 of these points are graded. So what that means is the extra 8 points are extra credit if you can get them. So if you get a perfect score, you'll get 83 out of 75, and you get to keep those extra points. Here's the bad news. First off, you have 90 minutes, so this is your time limit. The second caveat is that you will only be given one question at a time. So what that means is that the first question will pop up, and there will be nothing else. And it will not go away until you put in some answer to it and move on. You may not go back and edit your answer. So if you don't know the answer, choose something, move on. Okay? Now, that is part of the reason that this exists. You do not need a perfect score to get 100%. You can miss a few questions. So if you skip a question you don't know, that's okay. The other caveat is that I know that people have Discord. So if people are around on quiz day or exam day, and you get a question you don't know, the temptation to go into Discord and ask, hey, I got this question, I don't know the answer. Does anybody know it? Sure, you can use that resource, but mind the time, okay? There's going to be a lot of questions, and I know how Discord works. You might type a question in, and nobody will answer, and you'll be sitting there waiting while your timer is ticking down. And I'm laughing because this sort of thing has happened in the past to me. Not with, like, an exam, but for, like, I needed something by a deadline, and then nobody got back to me for an hour. And that's obviously not okay when you have a 90-minute time limit. So what I'm trying to say here is don't rely on other people to take your exam. Don't copy and paste all of the questions into Discord, because that's not going to really help you. That's going to waste a lot of your time, okay? If you have to do it once or twice, I'm not going to stop you. If you have to do it for every question, hoping that somebody will answer it for you so you get 100%, one, those people are going to get mad at you real quick, and two, you're going to run out of time. So know the material. That's the best way to do well on the exam, okay? And yes, you can get over 100%. You can get whatever 83 over 75 is, which by design should be about 110%. 110.6. So that is the highest score that you can get. There will be a button at the very, very bottom of the quiz that says submit. And if that is there, I'm going to preview the quiz. I will tell you, under no circumstances, push that button until you are done. I know on the old quiz method, it would tell you to go to the next problem and then, like, submit at the bottom. And if you hit submit, it would end your quiz and just submit blank for everything else. I don't know if that is the case for the one question at a time format, but I will debug it and preview it for you over the weekend, because that's basically what I'm going to do all weekend, is make sure this works. And that will appear on Monday. So again, remember, the exam is Monday, and I got to do dates in my head. 15, 16, 17, 18. And that goes from midnight. Jesus, you guys don't do military time. I'm sorry. Hold on. So midnight to 11:59. It will be open the entire day. You need to start your attempt within that window. If you start your first attempt at 11:58, it will be closed before your second attempt. Don't put the exam off, okay? Finally, I did tell you at the beginning that if you needed leeway of about 1 day or so, please let me know. I can open the exam earlier or later. Earlier is probably worse, but later I can definitely do. I know one student asked me, like, hey, I work. Is there any way I can do this on Monday? And, like, sure, I can do that on a case-by-case basis. So if you have a reason that requires you to do the exam offset by 1 day, let me know. If you need more time than that, like this weekend just absolutely doesn't work, I can let you do it with your NQA coupon. Send me an email. We'll talk it out. Okay? That's it for today. Thanks for watching. I realize quantum mechanics is insane and weird, but as you study this and dive into it a little deeper and put some more time into it, it's like riding a bike. You'll get there. Okay? And it might take you all quarter. But that's the important part, is that as you slowly start to think about this, it'll begin to make sense. And then the secrets of the universe will unlock themselves. All right. Thanks for watching. Have a wonderful weekend. Stay safe, stay healthy, stay home, and good luck on the exam. We're all counting on you.